As you all know, my name is Sandra Alexander, and today I'll be doing an introduction to magnetism for you all. To start off, let's brainstorm together on what we know is magnetism. So, can anyone tell me what is magnetism, or what's a magnet?
Like how some iron or metals are attracted to magnets, or
Yeah, that's true.
Perhaps like magnetic force or magnetic field.
Yeah, that's true. That's what I'll be covering in the presentation. Does anybody else know anything about magnets? I'm sure you all do recognize the first magnet up there, and I'm sure you've played with different types of metals when you were kids, and you've noticed that attraction between different poles, and then how magnets are made of south and north poles. I'm sure you've also seen on compasses how there's a north and a south pole on a compass, and even on the Earth that we live on, there's a north pole and a south pole. And as Alex said, only certain metals can be magnets, especially if they're iron, and it really depends on their molecular properties. There are other metals, including cobalt and nickel and iron too, that can be attracted to metals even if they are not magnets themselves. You may also be thinking of the opposite poles of the magnet and how it's like the opposite charges that we've seen in electrostatics when we were playing with electricity. We saw that there were positive and negative charges, how they are attracted to each other, and how the same charges, so positive and negative, they repel each other. This is similar to magnetism, but it is not the same, as in magnetism there is always a dipole together, a north and a south pole, but in electrostatics you have two charges, the positive and the negative charge, that can exist individually and don't always have to be together. If we separate a magnet in two, we will not have two monopoles, as in one part that's the north pole and then the other part that's the south pole of the magnet. It will just become two different magnets that each have their own dipole. Next I'll be talking about magnetic fields. Each magnet has its own magnetic field that is around it. Magnetic fields are vectors, so they do have a specific direction, and in magnets they usually lead from the north pole of the magnet to its south pole. An experiment that helps us visualize the magnetic fields on a magnet is dropping iron fillings on a bar magnet like in the picture. You can see how it's sort of circular and how the magnetic fields start by going out and then back into the other pole. And as I just said, it should always go from the north pole to the south pole. As you can see, they always form closed loops, and the more crowded that the magnetic field lines are, the stronger that the magnetic field is. Magnetic fields can be represented by the vector V, and their magnitude or strength can be measured in Teslas, that are 1 Newton per ampere meter. Compasses follow the magnetic fields of magnets, so their pointers will also always point to the south pole, as the magnetic fields always lead to the south pole. You may be thinking, well, we use a compass, and our compasses always point to the north pole of the Earth. Well, this may be true, but this is just our conception of the north and the south poles of the Earth that are wrong. The north pole is actually the south pole, and the south pole is actually the north pole, if that makes any sense. Next, I'll be addressing the link between electricity and magnetism, which is called electromagnetism. In 1820, while Hans Ørsted conducted an experiment in front of his students using a compass and an electrical circuit, he noticed that as he brought the compass closer to the circuit, there was a force that was exerted on the needle of the compass, and it changed where it was pointed because of the circuit. And that also changed according to the current. He then established that there was a link between electricity and magnetism, and discovered one of the fundamental principles of electromagnetism, that an electrical current produces a magnetic field. When a current runs through a wire, the magnetic field surrounds the wire like we see in this picture, and it forms circles around the wire. Using the first right-hand rule, we can determine the direction of the magnetic field and the direction that the current is moving in. If we try to wrap our right hand around this circuit here, we'll have to do like this, and we'll see that our fingers will be matching the magnetic field and the direction of the magnetic field, and our thumb will be pointing down, and that is also the direction of the current. So Oersted discovered that currents and their magnetic fields influence the magnets around them, so that does mean that magnets should also have their own influence on currents. One of the influences of a magnetic field on a current is electromagnetic induction. It is when a current is induced in a wire by a magnetic field. It was discovered by Michael Faraday that only changing a changing magnetic field can induce a current in a wire and not a constant one. His law of induction claims that a changing magnetic field will induce an electromotive force, which is what causes the electrons to move and form a current, and this happens in a loop of wire or in a solenoid. The area of the loop, the strength of the magnetic field, and the angle between the magnetic field and a line perpendicular to the face of the loop will all affect the magnetic flux, which is practically the amount of the magnetic field that flows through the current. Now I will do a demonstration to show how these three things will change the magnetic flux in the current. So, as you can see here, this is these are different loops of wire connected to light bulbs, and we'll be able to see the strength of the current according to the magnetic field that is given out by this wireless phone charger. The wireless phone charger will induce the current in compatible phones and charge them rhythmically using the magnetic field. So with this first one, since the area is large of the loops of the wire, and since it matches the area of the wires inside the charger, it seems as if the light bulb is pretty strong. If we compare this to smaller ones, it is less strong than the first one, and also the angle and where we place it does matter. It matters way more than we do with this one because it's bigger. We can also see the change in the angle here, how here it's the strongest, and then if we move it there it gets weaker, and right beside each other it doesn't work anymore. And here too, how it is distributed between the two. So that marks the end of my introduction. We covered magnets, magnetic fields, and some of the basics of electromagnetism, and we will continue to cover these theories and more of the theory behind electromagnetism and learn how to apply that to our future projects. Thank you.